Hello, how's it going?
Richard, let's do that again, guys. How's everyone doing? Good?
Yeah.
Woo.
Excellent,
right.
Excellent. Pleasure to be back here in Devox. Pleasure to be back here in Belgium. Lovely to see so many people in the room.
Pleasure to drink some Belgian beer.
My name's Richard.
And I'm Raoul.
The title of this talk is Java Collections, The Force Awakens. So, quick hands up, who saw the new Star Wars film the other year? That's a good number of people. If you didn't, don't worry. We're not doing any plot spoilers, so you're still fine. But you should watch it. But perhaps more relevantly, why talk about collections in 2016 at all? They're like an old thing, a thing which we're all familiar with. We've been using collections for a few years. But I think it's one of these things where, even for things which are mature and very good, there's still room for evolution, there's still scope for improvement, even if what the improvement looks like afterwards can be very different from where we started. So we're going to be talking about some new ideas when it comes to collections. Firstly, we're going to talk about a few kind of very, very simple API improvements that you can use in the Java Collections framework today. Then we're going to talk about things like persistent and immutable collections, so things which Java hasn't historically supported very well, but which you can get the benefit of through some third-party libraries. And we're going to be looking at how they're useful to you and how they can be implemented. And then we're going to talk about a few kind of different performance improvements, different performance discussions related to collections at the end, so hopefully that's fun.
So we've got some bad news, spoiler. Unfortunately, no lightsaber yet in Java to help us develop, but there's a few other good stuff coming up. So what we're going to kick off is to review a few of our favorite bugs with collection. And the first one, obviously the overbound error, or the array out of bound. And this is what happened to this little poor machine here. Had a little out of bound exception. Or maybe drank a little bit too much Belgian beer. Who knows?
Who knows?
Who knows? But everyone's familiar with this bug. So what we're going to talk about here is two bugs that are maybe a little bit less common. The first one is the concurrent modification, and then the CheckinAct pattern. And to illustrate, we'll look at a little bit of code, Richard. So what have we got going on here?
Well, you've got your array of Jedis, then you're going to print out your Jedi's array, and then you're going to loop over it, see if the Jedi's name begins with a lowercase letter, and then remove it if it does. That looks good. What happens if we run this code?
Well, the code compiles, so it must be working.
Oh, lovely.
Let's ship it. And boom.
Nasty. Concurrent modification exception. Why is that happening, Raoul?
Well, it's interesting to see what's going under the hood here. We've got this nice little for loop here, which is actually abstracting an iterator object under the hood. So we've got an iterator object here that is responsible for iterating over the collection, and separately we've got this collection. So just to see a little bit what we've got going on here, I'm just going to write it the vintage Java way.
Excellent.
So we've got an iterator object here, and we constantly poll to see if there is a next element. If there is, we fetch it. And the problem we have with this code here is that we've got two objects that are acting on the same source. There's iterator here that needs to keep track of an index, what current element it's currently iterating over. And then you've got a collection here separately that's going to remove the element. But they're not communicating between the two. So we've got a sort of the unsynchronization problem. So, and hence we've got this concurrent modification exception here that tells us, hold on, there's some behavior here that is unpredictable. Those two objects here are out of sync. So instead what we do in Java is to make use of the iterator object that is responsible for managing the iteration and the removal of the elements. So in my case here, I'm going to have the iterator. And if the Jedi here is lowercase, then we use the iterator object to modify the source. Okay? So the collection here, in this case, we don't need it anymore. So if we run this code, what we'll see is we get the correct behavior. Okay? Because we simply use the iterator object.
So that's great. There's no concurrent modification exception. But you've kind of used an iterator here. It's not really 2004 anymore, is it? Iterators a little bit old-fashioned, and not old-fashioned in a good way like a fine wine, more in the kind of, you just don't want to use it anymore way. A rotting piece of wood.
That's a fair point, and this is where APIs can evolve as new idiomatic patterns come up that may be error-prone. So who in this room is using Java 8, out of curiosity? Awesome. Well, quite a lot.
The same people who went to see The Force Awakens.
That's true. Well, in Java 8, a couple of methods were introduced on the list interface, or actually on the collection interface, to make things a bit more convenient. And one of them is called removeIf. And what that's going to do is a mutable removal on the collection if the element is matching a given predicate. So in our case, given a Jedi, we want to check that the Jedi here, its first letter is lowercase. Okay?
Awesome.
So let me just delete this code, and you can see, it takes us a few lines. We can remove this, so code here is cleaner. We've got a nice method here that indicates precisely what it's going to do, and we've delegated the internal implementation, the checking, to the library. So that's great. Reduce the scope for bugs.
Awesome. Got rid of our iterator, brought things up 2016 vintage.
So that's one of the common bugs, and there's another one that's fairly interesting, Richard, called the CheckinAct principle. So, because we all love Star Wars, and because your favorite movie is The Phantom Menace.
What are you talking about? That is awful. That is awful.
Richard's favorite movie. And what we're going to do here is to watch this movie lots of times just to support Richard, in this. So there's a bit of
100,000 times watching The Phantom Menace. You'll lose your mind.
Big data here, big data.
Big data.
So,
too big for Excel, maybe.
So let me walk you through this code a little bit so you see what's going on. So we've got this sort of hash map here that's going to keep track of the number of times we're watching the movie, okay? And we initialize it to 0. So what we're going to do is to sequentially increment the number of views to this map to recall how many times it's being viewed, okay? So don't worry about this executive service stuff. We'll look at it in a second. So sequential add, very straightforward. We just pretend that we watch this movie quite a lot, and then the add one view here gets the number of views, check that it's not null, so we need to check whether that's been initialized. And if it's been initialized, then we can actually increment it by 1. Okay? So very nice, straightforward code. So let's run it, and if we run it, we'll see that actually we get 100,000 views. Perfect.
Well,
deterministic,
you say perfect.
Predictable.
Deterministic, but simultaneously terrible. Okay, so what about the concurrent version of this code? What if we try and run that instead?
So Richard, we need to go web scale. So about scalability these days. Let's go concurrent. So what we're going to do here is just a method that's implemented a little bit differently. What that's doing here is to use an executor service under the hood. So we'll have a few threads, and we're submitting jobs to that thread pool. And the job is essentially take the hash map and increment the count. So what we're trying to do is to simulate that many people concurrently could be watching the movie. Okay? So that's just sending job to the thread pool. So let's run this code. This looks pretty good to me. It's compiling, so let's ship it.
Awesome. Ooh, that's less than 100,000. So this is good news. If you go web scale, less people watch The Phantom Menace.
That is true. But Richard, we want to write code that is deterministic, predictable, we can test it. This is not good.
I know what we can do. There's a concurrent hash map, right, in Java. So why don't we just use the concurrent hash map? I've heard if you prefix class names with the word concurrent, it fixes all your concurrency problems.
You know what? That's a great tip. Let's just try this out.
Let's see if that works.
So let's run this.
Ooh, it's actually worse.
That's a bad tip.
That's a bad tip.
That's a bad tip. Don't do that.
That's a bad tip. So let's go and have a look at this concurrent add method. What's going on there?
So concurrent add, submitting job to the thread pool, submitting this add one view. Richard, I know the trick here.
Okay.
Instead of using concurrent, why don't we use synchronized? Synchronized is going to fix everything, right? Makes things atomic, I don't know what this code does, but synchronized feels like the right thing to be doing.
Build a big, beautiful lock around that hash map.
It's working.
It does work. But it's also basically single thread at that point, isn't it? That's the real problem here.
So we're not going web scale.
We are not going web scale.
So let's look at this code a little bit and try to really understand what's going on. So we have all those stars here that are being submitted to the thread pool. and just going to add one view. What let's take as the argument is the movie views. So that's our hash map, right? That's the sort of this global state here, the hash map that is being shared around. So we've got some shared mutable states. And what this operation here is doing is a compound operation that has several steps. First is to look up the number of views, check that the number of views is not null. If it's not, we're actually going to act on this and update the number of views. So this is why we call this the CheckinAct pattern, because we've got the condition, and then based on that, we will act. But because it's a compound operation, we could have arbitrary interleaving happening on any of the stages and threads that are overriding each other's work. And this is why we get a data race here, and the result is unpredictable.
So you're saying that two threads at the same time both read the views, and then they both try and add one to each of their different view counts, and then some of those updates are lost.
Indeed.
You know what I've heard of? There's this replace method, isn't there, with movie views, right? With concurrent hashmap, and that'll return you a boolean if it's succeeded or not.
So this is the replace method, and that's the signature. And what replace is doing here is to actually implement this idiomatic operation, right? I decided that, well, first we've got a value here. We want to check that it's the same value, and if it is, atomically replace with a new one. If it's not, then this returns false, and we're going to have to try again. So what we want to implement here is a mechanism where we use replace to replace the value until we succeed. Okay? So we will loop. We will get the views. Okay? We're going to check that the views has been initialized. Okay? And at this stage, what we want to do is to replace it with an updated value. So if we manage to replace, so we take the movie, we take the current view, so this is what I'm expecting. And if we get the same value, then at that point, we're going to replace it with this updated value and break. So let's get the number of parentheses right.
So there's a pattern that requires a lot of patience. That code's got to try and try and try again until it succeeds.
But Richard, this code looks a bit complicated, so let's just check to make sure it's actually working.
Ooh, it does.
It does.
Amazing.
It's a bit painful. It's really, really verbose, very error prone. I really don't want to be writing this.
Yeah. But there is a new friend in Java 8, right? Compute if present.
And compute if present is implementing this pattern where you want to compute a value if it's been initialized. So what it takes here is a lambda expression that's going to indicate what's the recipe to update the value in the map for that given key. So the recipe here is exactly the same one here. We get the views and we add one to it. Okay?
Awesome.
So let's get rid of this and run the code again to make sure things are working. But already you can see it's much neater. The code here, the name of this method indicates what it's going to do, compute if it's present, and we've delegated internal implementation details at the library. So code here, we reduce the scope for bugs again, thanks to API improvements.
Excellent.
Awesome. But that's not the only thing that's been added to, well, what we've talked about so far is things that are existing in Java 8. And there's a few goodies that are being introduced in Java 9. Ooh. There's a few improvements to the stream API, to the completable feature, to optional, which we're not going to talk about. But the, what is going on here with my shell? Let's run this again. One of the things that's being added to Java 9 is collection factories. So traditionally, it's quite a pain to create different collection objects. So let's say I want a list of string, a bunch of CDs.
Awesome.
I'm going to create an array list. I'm just going to do it the old school way for a little bit here. And we get an empty array here. By the way, this is called a JShell, so it's a REPL that's been introduced in JDK 9. Mark Renhall was showing a demo in his keynote. So that's quite nice to be able to play with different APIs and get a feel for how they work. So what I want to do is just to initialize an array list and add 2 elements to it. So maybe I'm going to add Brussels to it.
That's where you were born.
That's where I was born. And in Belgium, we love the Welsh people, thanks to the football. So we're going to add Cardiff into it.
That's where I was born.
That's where Richard was born. And if we look at the cities, we can see we get an array list with 2 elements. It takes quite a lot of work just to create a simple array list. And there is something else that was introduced here, arrays as list here. And I could say London. But that doesn't really work for a set. Doesn't work for a map. What if I want to have a convenient way to create maps and sets? We don't actually have that facility. But Richard, you know languages like Groovy and Python, they've got syntactic sugar for this.
Collection literals, like bracket, Cardiff, Brussels, bracket, something like that.
Exactly like this syntax, actually, right, like this. Why can't we have this in Java?
Well, there's a lot of costs when you do these kind of things, aren't there? There's a lot of time that could be spent implementing other features. But what was added in 9 was collection factory methods.
So it works like that. So you just say, let's start off, boom, I'm getting a immutable list that is returned. If you want to set, you can do the same thing here. We're going to say London and Cambridge, actually, my favorite city. Cambridge. Right, so we get a nice convenient way of creating different collections. And we can also have a map. So let's import statically all the goodies in the map. And let's say I've got a map of different entries. I might have an entry here that tells me Brussels. How many people are there in Brussels, Richard?
1.139 million.
1.139 million. How many people in Cardiff?
341,000.
We win.
Yeah, not at football, though.
Not at football. Right, so this is sort of a nice, convenient way to create different maps, and you can see here we get a nice little map that is produced as a result. Okay.
Awesome.
So nice, convenient improvements to API that were introduced in JDK9. Fantastic. Cool. So that covers a little bit the different topics here, but one thing that is interesting to look at is sort of the CheckinAct pattern that we showed. You may think, actually, it's a really contrived example. But there's some research that actually performed some static analysis. So they took a bunch of open source projects, and they were checking whether this pattern actually happens in real code and whether there are bugs. And they found about 280 bugs for the CheckinAct pattern in projects like Cassandra and Lucene, right? So
not just toy projects, real big open source projects that people genuinely use.
So it's great that we've got new API improvements here to reduce the scope for these kind of bugs. So if you're interested more about Java 9 updates, there's a link here that you can check out afterwards. So we've talked about API improvements. What we're going to do now is to talk a bit more about data structures and possibly sort of improvements that could be done to the collection structures. So Richard.
So I think it's always helpful when you're thinking about a big topic area like collections to try and categorize or break up that topic into different areas. And one of the ways that we've thought about it in terms of splitting these things up is you can first of all think about mutable versus immutable collections. So collections you can add or remove elements from, change the state of. And those mutable collections could both be unsynchronized, just like array list, or something concurrent, like the concurrent hash map we saw earlier. And then we can think about unmodifiable views, which are kind of a wrapper around mutable collections. So if we firstly look at our mutable friends here, very, very popular, very, very commonly used, array list, hash map, tree set. These are collections which, when we say memory efficient modification operations, we mean they're just updating their internal state. They don't need to return you a new copy. They don't need to do anything like that. They can be thread safe, but it takes a lot of design, a lot of care to get them that way.
But Richard, what tricks do we have, if we want to be able to prevent those accidental updates? What can we use in Java right now?
Well, something that's been in Java for ages and arguably is quite an underused but useful feature is this unmodifiable concept. So the collections class has some factory methods for unmodifiable lists, unmodifiable sets, blah, blah, blah. And what they do is they allow you to wrap a single value, a single collection up, and give you an unmodifiable view on it. So if you try and add something, so here, for example, we're adding Darth Vader into our list of Jedis. Darth Vader's not a Jedi. So we throw an unsupported operation exception and stop that modification. But obviously, you can still modify the underlying array list. Now, in some senses, this is really useful, right? You may well want to have that modification. But there's a little problem, isn't there?
Well, to be honest, this is really cheap to create to get this view, so that's one benefit. But the problem is a little bit analogous to Death Star. So Richard really wants to have a Death Star at home. And the problem with the Death Star, there's like one tiny little flaw, right? You can still...
Thermal exhaust port, a little thermal exhaust port on the collections, which is, once you've got that reference to the underlying mutable data, you can modify it, but you can break the invariant that you might expect to have.
So that might not be the right tool at hand, but Richard, there are alternatives, right? I hear all those functional programming languages, they really talk about something called immutability, right? What's that about?
Good question. So there are different types of immutable data structures. So these are data structures which you don't change that reference. Once you've handed out that reference, you don't update or modify the state. Now, these are very useful from a concurrency point of view because you can hand off different instances of these objects, and because they're not going to have modified state, they are not going to have any data races with that modification of state. It's very useful for holding a reference on an object. It doesn't have that Death Star problem where one person can completely undermine your invariant that you're maintaining. And the simplest version is non-persistent immutable collections, right? So by non-persistent, we mean when you add a new element in, they basically copy the old values in, add the new one in, carry on going. Nice and simple.
Probably my favorite characteristics about the immutable structure decided I can convert to something more efficient, right? If we think about something like a mutable tree, there's a bunch of nodes and they're pointing at each other's. That takes a lot of memory overhead. But if you know that tree is not going to be changed, you could convert it into a single array and use an offset-based strategy to look up the elements. So those are the kind of things that are possible using immutability. But Richard, sounds a bit useless if we can't modify it. What are we actually going to do? The real world, we actually need to change objects, right? So what are we going to do?
Well, one collection API, which has got both immutable and mutable versions of collections, is what used to be called the Goldman Sachs collections, is now the Eclipse collections. And what they have an approach is, Java has this list interface, which is a list interface for immutable lists. So when you add something, it modifies the underlying version. But they have a list iterable interface that is just the read-only methods on a list that lets you hand out a read-only view. And then that can be implemented with an immutable list, which has a method on called newWith, which would return you a new list, or a mutable list, which would modify its state internally. Fantastic. So it is possible to help you incrementally migrate a code base, and an example library is something that implements those non-persistent immutable collections.
That sounds great.
But there is another option, which is the immutable and persistent collections option. And this is where a change in the source produces a new version of the collection, but they try and share structure, try and share the values with the old version of the collection, so you don't have the cost of copying all these elements every time you want to add one collection.
So let's look a bit more in details at this, right? Because when we talk about immutability in functional languages, there's perception that's really inefficient. We have to copy everything. And there's actually a few tricks that we can do to reduce that problem. So we have to go back in time. We have to go back to Lisp, Richard. Do you like Lisp?
I do, but the problem with Lisp is it's fun to program in, but the different bracket keys on my keyboard, eventually they just broke from overuse.
So I've got a new keyboard for you here. This is your new keyboard.
Oh, that's fantastic.
It's going to fix all your problems.
Awesome.
Anyone used Lisp in the past? Keep your hands up. Anyone still using Lisp?
Oh.
Come on, there must be one person.
Sure, there's one guy somewhere. Okay.
Must be Clojure these days.
Okay. Awesome nonetheless. Awesome nonetheless.
But what Lisp did, which is really fantastic, is to come up with this idea of a persistent list, aka called the const. And the basic idea with a const list, it's a bit like the Russian doll concept, right? You take the doll and you wrap it up into a new one and you wrap it up, or the Christmas boxing idea. So what we're going to do here is, whenever you want to add an element to a list, instead of having to change the pointers, it's actually wrap this element with the next one in the line. So let's say I've got a header here, so that's a new element that I like to add in. And I've got my tail, which is the other boxes. Well, I'm going to give you a new box with the head and the tail. If you want to update this again, let's wrap it again. And this wrapping technique here doesn't need any mutations, because we're always creating new objects around it. That's quite an important idea here, is that actually, if you want to provide an updated version, you don't need to modify it. You can create a new version that wraps the previous version. So we're sharing state with the previous version. So that's a key idea. So if we look at it from a more visual point of view, so we may want to also modify an element within a list as opposed to just append it. So let's say I've got this element here, C, and I like to change it to something. Let's say the letter D. So brave. So what are we going to do? Well, I'd like to provide an updated value for C. So that's going to be a new element called D. Unfortunately, B here is pointing at C, so I'm going to have to change this so it points to D.
Hang on. A is also pointing to B, so if you change B, don't you need to change A as well?
Indeed. So what's going on here is that we have to copy everything leading to the new element that we want to change, which we can then hook up to the next element in the list. So in this case here, we create D, we create a copy for B, we create a copy for A. Those are all linked up, and then we can share the tail of that list. And the previous version here is still independent.
So it sounds like what you're saying is, if the element's at the front of the list and we want to modify it or change it, we have everything after that we can share and it's nice and easy. If we have something that's, say, the last element in the list, or the last but one element in the list, it's not really giving us much of a win.
That's true. So the last element here, we still end up with a full copy. But, you know, there's a few other tricks, but what's something that's interesting to mention here as well, it also works for merging two intermediate lists. Maybe you've got some work being done parallel, you like to merge them. The only thing you need to do is to copy one side to the right-hand side, right? You don't need to copy the whole thing. There's a few issues with this approach. One is, yeah, if we need to modify the elements at the end, then we end up with a full copy, so that's not great. The other problem here, if we think about it, something like an array, it's really nice in terms of caching. The next element, its offset is very predictable, so the prefetcher can just take it, put in the cache. It's very cheap and convenient. But something like a linked list approach, each element is pointing somewhere on the heap, so we can't prefetch it and get the win here from a caching point of view. So it has poor locality, so that's one big problem from a performance point of view.
Randomly walking around memory is often, 1,000+ times slower than reading through memory in a nice sequential pattern as well. So there's a huge performance cost there in some respects.
So Richard, it sounds like the trick here is we want to be able to reduce the number of elements that we want to copy and reduce the number of time we have to navigate through this sort of chain of pointers. And there is we talked about this, but there is a sort of another data structure called the binary tree, right, which lets us reduce the number of navigation required to locate a element. But we need a trick, and the trick here is, well, if those elements are comparable, I can decide which sides to pick. If it's smaller than one side, I go on the left. If it's greater than the other side, I can go on the right-hand side. And by doing this, we can reduce the number of steps required to locate one specific element. And that means there is fewer copies to do. In this case here, if I want to modify the elements on the bottom right corner, what I can do is to create a new version for it, copy the parent, copy the grandparent, and then link that back to the previous version of the structure. So what happens here is actually I only need to copy 3 elements as opposed to copying potentially the whole tree. So that's an interesting property here. We get this sort of structural sharing with a previous version, so we reduce the number of copying required.
And you're saying as well we can use the same binary tree concept for implementing what Java would call a list-type data structure, by using the index that you're going to look something up as a way of defining order over these values, even if they're not comparable, right?
Precisely. But the issue here, Richard, is that, let's say we've got lots of elements in this list. We end up having, quite a lot of navigation to be doing still. So what we'd love to have is performance and the safety that immutable data structure provides us. We want to have the power of the Jedi's and the Sith together. Wouldn't that be fantastic?
Yeah, that sounds great to me. And you've got all sorts of different color lightsabers if you do that as well. So
Indeed.
It can't go wrong as a plan. Let's do it.
Let's do it.
How do we do it?
Well, a key intuition here is we can go beyond binary. We can go beyond just like splitting a tree into 2 parts. We could actually have more than 2 children, right? Some people have 3 children, 4 children. Why do we have to stick to 2? So let's go for more. More is better. So this is what we call a tri-data structure. It's called tri, not to be confused with a tree, all right? So that's the...
But I heard they originally called it a tree. That was the goal, to call it a tree. But then they said, wait, what's the difference between a tree and a tree? No, let's call it a tri. That's a much better idea.
Much better idea, and what it means is the branching factor can go beyond 2. So here's a sort of data structure that's quite useful for things like looking up the number of words that start with a prefix. And the key idea is we can use the edges. Edges are going to have a label, and they're going to be used to locate the leaf nodes. The information is only contained at leaf nodes. So if I want to find out all the words in the English dictionary that start with AC, I can navigate the edges, AC, and bam, I'll get the number of elements. Okay? So great data structure for the sort of a prefix search. But the beauty here is that we can increase the branching factor, which will help us reduce the depth that we need to navigate through. Okay? So that's the key idea.
Awesome.
So we can extend this idea to arrays. We've got this crazy thing here called a bitmap vector try.
Bitmap vector try? It sounds like a dental operation. There's teeth all over the place, blood all over the place, children are crying. Why do you want to make children sad, Raoul?
Well, in computer science, you always need to have some like fancy sounding, terminologies to bring up during parties and stuff. So that's probably what happened here.
Okay.
I don't know who's responsible for this. But what we're going to try and do is to extend this idea from a try, where instead of having strings for the edges that lets us look up the leaf nodes, we're going to use a bit representation of the index for the element that we want to look up, okay? So if I want to find the element at index number 45, I'm going to use the binary representation of 45, okay? So that's going to be the bitmap. What we can do with that is to use different parts of this bitmap to indicate which level in the try we're going to delegate to. So let's say the first 5 bit here are going to tell me what's the element at the first level. The next 5 bit are going to tell me what's the element at the second level that I need to be able to look up, and so on, until we find a leaf node. So we get a sort of efficient arithmetic operation here that lets us navigate to the leaf node where the actual value is contained. And that's the basic idea with the bitmap vector try, is that we use the bit representation of the index of the element so we can navigate the try.
So this sounds very theoretical in kind of concept. Is anyone actually using this kind of approach?
Well, so this approach is used in a lot of functional languages, like Scala has a persistent array implementation, Clojure has a persistent array implementation, and a bunch of libraries in Java also using that now. But there's a bit of a trade-off, Richard. The trade-off is, we've got this complex data structure. Here we used an arbitrary number of levels. So in our case, we were using about 5 levels. And 5 level means we actually only have 5 lookup to be doing. So it's near constant time to look up an element. So that's quite an improvement upon the binary tree, right, when we get the log n complexity.
And much better than the original linked list approach where we had order n to get up there.
Indeed, so we get a nice improvement. But there are trade-offs, right? Having a large branching factor means the iteration become really cheap. But if we need to update an element, suddenly we're going to have to copy every node leading to that element, so it's 32 every time, so we get quite a lot of copying going on. But we get a nice caching property, though, because we get 30-element array. And a small branching factor means that we get a higher iteration problem, so the depth is going to be larger, but we potentially reduce the number of copying required, because the nodes here are smaller. So 5 is sort of the magic number that a few libraries have adopted. And there's a bunch of projects available in Java, SP collection, there's a port of the closure data structure, a port of the Scala data structure, and Java slang. There was a talk about Java slang. We love Java slang here. Bring functional ideas to Java. Recently introduced a persistent array implemented through this bitmap vector try idea.
And I know the Java slang guys as well. The pull request is only very, very recently accepted on that. But they've done a huge amount of work on benchmarking and optimizing their implementation. So that's looking really positive.
Indeed. So we don't have performance benchmark here, but one interesting thing to look at is the memory usage of all those different collections. So we run a little experiment here. Again, we're going big data.
10 million elements. This actually might be too big for Excel.
Anyone uses Excel here? Anyone knows? I don't really use Excel.
Okay.
But here, if we want to store 10 million ints, so primitive ints, the memory overhead of that would be 40 megabytes, or 4 bytes for an int. If we use the box representation, however, of an array, so we're paying the overhead of having an object, we get 160 megabytes.
Outrageous.
Outrageous. But what's really interesting here is that actually, if we use an array list or this persistent vector from Clojure or the Scala port one, they sort of have equivalent memory consumption. In fact, actually, the Scala implementation has a smaller overhead. Now, that's a little bit puzzling, isn't it, Richard? But it has to do because the implementation of an array list, if it runs out of space, duplicates its memory, so you've got more elements available. So you're sort of paying the cost here for having some extra space in the case that we are overloading the data structure. So we're paying this cost here.
And the thing is, these numbers you're talking about are with heap being less than 32 gig, because we're talking about numbers with compressed OOPS switched on. If you have an even bigger heap, you'd have even larger pointers, and these numbers would be even larger for the array list over the primitive version.
So the interesting difference is those persistent data structures, they can grow dynamically, right? As you add a new element, you're only paying the cost for adding those elements. Something like an array list, if you're overflowing, you might potentially pay a higher cost where you have to suddenly create some new space in the data structure. So what are some takeaways here? Well, we believe immutability in general is good practice, and immutable collection reduces the scope for bugs by preventing mutable accidental operations. But unfortunately, there's always a compromise between performance and the safety benefits. But that's something that we see a lot of improvements with recent data structure, and the persistent arrays is one example of that.
Absolutely. So let's have a talk about some of the performance improvements that we've kind of seen in a few of these places. Now, everyone really, really does want some performance improvement, right? You want to go really, really, really fast. And in fact, we decided that in the context of this talk, we actually need to update big O notation, don't we? To have a newer, faster form of big O notation. So we decided that there was order n, linear time, order 1, constant time, and order hyperspace for when you want to go really, really fast.
So we can't wait to see in the Java doc order of hyperspace. That's the new thing.
Excellent. Now, the first thing we're talking about is, as you mentioned earlier with the primitive int arrays, that's something very, very simple. If you have primitive specialized collections, they use up a lot less memory, and they are much, much faster for both adding and removing things from. So Java 8 has primitive specialized streams in the form of int stream, long stream, double stream, and primitive specialized functional interfaces. And there's a bunch of third-party libraries out there. We mentioned Eclipse Collections earlier, Colaboke, and also the Agrona library that offer primitive specialized collections.
But there's actually improvements happening potentially in future version of Java. There's a project called Valhalla that looks at having primitive specialized generics. So we can get a lot of those improvements in the JDK itself. And if you've been using Java 8, you may see things like functional interfaces, where you've got primitive specialized functional interfaces, to make up for this deficiency. So there's a wider research being done here to get some of those benefits, both at the language and the JDK level.
Awesome. Another very, very simple existing collection improvement is that Java 8 started lazily initializing collections. So there are loads of places in code bases where things like empty array lists are passed around as a potential value, or empty hash maps get initialized with nothing ever added to them. An example might be, say, an API that used HTTP GET parameters and put them into a hash map and then never had any parameters, so passed them on. And Java 8 added very lazy initialization, so the backing array in the array list and the backing array of entries in the hash map never gets initialized until you actually add the first element in. So reduces the memory consumption and also reduces the memory allocation rates for things like this where they don't get used.
So simple, but effective, and there's a bunch of other improvements that have been made in Java 8, specifically with Hashmap. Come on, Richard. Let's do a bit of you to speak here. Let's do it at the same time. I'm going to say map hash we want together. Ready? 3, 2, 1. Map hash we want. Fantastic. So let's talk about Hashmap a little bit here.
Excellent. So very basics of hash maps, which I'm sure everyone's familiar with, but let's just mention it anyway. We have a backing array of entries, and we want to put a key into that map. So we hash the values in that key, we get a hash code, and then we apply a modulus of the length of that array, and that gives us a slot to put us in.
But hold on, Richard. I heard Chewbacca is Han Solo's best friend, and they're such good friends that they're going to share the same hash code. They're the best buddies.
Really? That's awesome.
What's going to happen?
Well, you get a collision, don't you? You get a collision. Sometimes being really, really good close friends, it's a bit too much here. So, once you have a hash map with a collision, you need to have some strategy for saying, how do we deal with collisions? And the general approach that people talk about is chaining versus probing. So chaining strategies are, you have a little data structure at each node to put things in, and probing strategies are where you store things inline in the main backing array, and you have a probing sequence. So you say, oh, I'll just look at the next element or the next element, or I'll have some function that tells us how to find the elements. And the interesting thing with these things is that you get a lot of terminology confusion here. You get probing, chaining, open addressing, closed addressing, all sorts of things. But it doesn't really matter. It's like this difference here between Palpatine and Darth Sidious. They've got different names, but they're really the same guy.
Equally evil.
Equally evil. Look at that face. That's an evil face.
It's an evil face. And the responsible for all those terminology is the academics, right?
Yeah.
Really sorry about this, but if you hear about close addressing, open addressing, and open hashing, close hashing, it's all under the chaining and the probing category, so it means the same thing.
The best thing about this terminology confusion is they've used open and closed to mean the exact opposite different things, depending upon whether it's addressing or hashing. That's awesome confusion.
But Richard, in Java 8, there's been a few improvements to the Hashmap internal implementation, specifically with the chaining strategy.
Yeah, so Java uses a chaining-based approach. Now, historically, this was a linked list chain. So if you have a collision, it plops them into a linked list. But there are other data structures you can use to make that lookup. If it's, say, a comparable key, you can use a tree-based lookup or something like that. And that, as you say, was introduced in Java 8. So it historically maintained a linked list. Now, if you have a high collision rate, you get an order n lookup. So the change in Java 8 was to change to use a tree-based data structure. But they don't go for a tree from the beginning, do they?
No, it's interesting because they've got a dynamic strategy where the hash map here converts to a tree implementation if the number of elements are growing, which means potentially would reduce the number of iteration required. But Richard, we've got those two strategies here. We've got the linked list strategy, we've got a tree strategy. We need a winner, right? Like, in general, we need the best implementation. Which one is the best?
You want a winner, you want a massive lightsaber battle between the different Hashmap implementations. Well, let's have a look at what's really going on here. I mean, I did a few benchmarks here. And in fact, first, before I wrote any, I had a look at a lot of benchmarks on the internet. And those benchmarks are what I'd call Jar Jar benchmarks. And Jar Jar benchmarks are a lot like Jar Jar Binks. They're not useful to anybody at any point in time, ever. No modeling of the different factors that influence performance. Things like just calling a get on a single key for a map of size 1. Now, there's actually a lot of different trade-offs that you have when looking at different collection implementations. So first, let's have a look at the difference between the different implementations in Java 8. So I started having a look at what happens when you have looking up keys in increasingly large maps. And what I did was chose the opportunity to see if the tree-based strategy worked by taking comparable or keys that don't implement comparable and are otherwise different. And the red bars are the ones that don't implement comparable. And you can see that as it scales up, you get a very, very significant improvement in the lookup time. So that works really, really well at high collision rates, like here's 60% of the keys collide with other keys. But if you have very, very few collisions, this kind of optimization doesn't really make much difference. So depending upon what your use case is, it may have either been a huge win or nothing at all. The other kind of trade-off that we sometimes see is probing versus chaining. Now, we didn't come up with terminology. This is a PG-13 talk. But we do need to think about the difference between probing and chaining. Normally, probing maps have lower memory consumption because they don't have to have this supplementary data structures going on. And in fact, if you get very, very few collisions or small maps, probing often completely destroys chaining as a strategy. Looking up in the map, very, very hot, just a straight array, boom, 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 can be 91% faster. But if you get really big maps with really high collision rates, probing scales really poorly because you end up having these long chains where you probe down the chain and fail and fail and fail and lots of collisions. So sometimes they can be much, much slower, like 1,000 times slower in some cases.
If you're wondering if probing is used in the JDK collections at all, there's actually one implementation of Hashmap here called Identity Hashmap. They use a probing strategy.
Exactly, yeah, very fast, very low memory consumption. If you want that kind of identity-based key equality concept, great, use Identity Hashmap. But really, there's no clear-cut winner. The JDK implementations generally try and trade off the worst-case scenarios. They try and keep your worst case not so bad. If people have hash codes that always return 1, it happens, then they won't fail quite so badly. But third-party libraries often pick probing-based strategies, where you'll find they'll often win over the JDK collections if you've got smaller maps with really, really well-distributed hash codes on their keys. So let's look at a couple of conclusions, shall we, to wrap up the talk. Collections are improving both on the safety side and the speed side, right? So we looked at how things like persistent and immutable collections can really, really help you make things safe. They give you that immutability characteristic that a lot of people want. And they're not as fast as they're not as slow as they used to be in the old Lisp days. Implementations have improved massively over the last 30, 40, 50 years. And even existing core library collections, which have been around and are really mature, like Hashmap, have improved their performance over time as well. Now, I'll give you guys an opportunity to ask any questions, and if you want to ask them on Twitter, if you don't want to shout out or find the microphone, you can tweet on #JavaForceAwakens, and we'll answer your questions as we go along. I hope you really enjoyed the talk today. It was a pleasure speaking to you all. And Raoul and I run a training company called Iterator Learning, where we run training courses looking at Java 8, looking at reactive and asynchronous Java, and a general kind of software development masterclass bootcamp type thing. Now, just to incentivize you to ask some good questions, Raoul has a few free copies of this mini book on introducing Java 8 to hand out. So
come down, there's only 5, so if you want one, come and
talk to us afterwards. Thank you very much. Does anyone have any questions in the room? I literally can't see anyone.
I can't see, but please use the Twitter hashtag here. We're going to look at Twitter in a bit and reply one by one to your questions, if you have any.